Okay, welcome back. Just one announcement. I managed to turn off all the air conditioning since many of you requested it. In any case, if the temperature becomes hot again, just let me know, and we will find a combination of them that doesn't make the room as a fridge. So, for the second talk of today, we have Waltraut. Is that correct? She will speak about what is the three-level string theory. Please take it away.
Okay, thank you so much. I want to first say thank you that I have the opportunity to speak today. I'm going to be talking about a paper that I wrote with Jean and Leonardo, who are both in the audience, and it was put onto the archive just under 2 weeks ago with, of course, the same name of this talk. And basically, we all kind of know, hopefully at least, that at long distances, gravity is universal. So it's just described by classical general relativity. But we've, over the many, many years as theoretical physicists, realized that trying to UV complete it is extremely hard. And the only real theory that we know of that so far does this is string theory. So at this point, one could then think about, well, maybe is string theory the only one that does this? Or what makes it unique that we were able to find this? And so this being a Bootstrap conference, we want to look at this question in a Bootstrap perspective. And what we want to look at is see what 2-to-2 scattering of gravitons look like. In this particular case, we'll be looking at 10-dimensional maximal supergravity, and want to see where does string theory fall in it. And then to find out the question, in some sense, does everything have to look like string theory, or can anything happen in reality? And string theory is just a random choice that we found. So let's start. So the main question I'm going to start with, and a lot of you hopefully will be familiar with the methodology, so I'll try to go through it quite quickly, but please stop me if you have any questions. So we'll be doing S-matrix bootstrap. And so the first question is, what does an amplitude look like in maximal supergravity? And in particular, and let me stress here, we'll be looking at everything at tree level. We want to look at 2-to-2 scattering of gravitons. In maximal supergravity. And so when I say maximal supergravity, I mean there's two different types, but because we're looking at tree level, both 2,0 and 1,1 give us the same answer. And the reason we want to look at maximal supergravity, next to the fact that this is a great playing ground for closed string scattering, is that we don't actually have to take a 4-point amplitude of gravitons, which sounds really hard. And instead, because of supersymmetry, we can reduce down to a scattering amplitude of scalars that are in the same multiplet of the gravitons, and this makes everything a lot easier. So if we have an amplitude of scalars, it needs to have the following properties. So the first one is we assume analyticity. In other words, the amplitude, if you look at the complex S-plane, where S is the usual Mandelstam variable, then the amplitude is going to be analytic everywhere except for possibly on the real axis. And because it's tree level, it'll only have poles on the real axis that correspond to some kind of interchanges of particles. Then we also, and this is very uncontroversial, of course, we have crossing symmetry. In other words, the amplitude will be symmetric under the exchange of S, T, and U, the three Mandelstam variables. Then we have unitarity, which can basically be, which in our case comes out to the fact that we can decompose the amplitude in terms of its partial waves. And in particular, if you look at the imaginary part of the amplitude, this is then given by a sum over a bunch of exchange spins where because we have this kind of symmetry, only even spins come through. And there's some numerical factors, but the important part here is the spectral density. So this part here is the Gegenbauer polynomials. So they're basically, since we'll be working in 10 dimensions, this is basically the analog of Laplace Legendre polynomials that we have in 4 dimensions. But this here is the spectral density, and unitarity tells us that it is bounded. And in particular, the one that we need is that it's bounded below and is therefore positive. There's also an upper bound on this, but that is irrelevant since we're working at tree level. And then the last one, and this one might need slightly more explanation, is the Regge behavior. So in this case, it is relatively uncontroversial to say that an amplitude generically would grow as s squared. In other words, if you take s going to infinity at fixed negative u, usually we can definitely say, because we have graviton scatterings, that it's better than s squared. But we're going to assume that the graviton itself regizes, not sure if I can say this word, regicizes, or is part of a Regge trajectory. In other words, we don't have just gravity on its own, but we also have, it's connected to the rest of the states. And that will make the Regge behavior slightly better. So this would tell us that the amplitude, that this would converge. In general. But this is what holds for the gravitons. And remember I said that we'll be looking at the effective scalars. And the effective scalars help us in that they improve this Regge behavior, okay, interesting, by a power of s to the 4. So in reality, if we're only looking at the amplitude of these effective scalars, then let's see, ooh, that was nice. No. Well, okay. This is a 2. S, you can't even see it. Anyway, s squared times the amplitude goes to 0. Yeah?
I thought that due to supersymmetry there should be an s to the 4 somewhere, because the s cube comes from the phase space in 10 dimensions.
Yeah, so the amplitude of if you only look at the scalars that are being exchanged, then the S matrix that you get through this would go as s to the 4 times some amplitude. This whole part of the amplitude has to be better than 1 over spin 2 effectively, so 1 over s squared. And then if you take out this s to the 4, you get this. So it's better than by 2 factors effectively of s squared.
Yeah, so the m that you defined below for unitarity is what? The scattering of what?
So this would depend on if you're looking at 2, 0, 1, 1 supersymmetry. 2, 0 is the easiest one to look at, and then this would just be effectively the 2 scalars that you have in the supermultiplet of the graviton. So they're on both sides of the supermultiplet, and if you take this 4-point function of it, then it reduces very nicely, and supersymmetry basically tells us that there's only one amplitude for all the superpartners. And they're all related in some way, and the one that's nicest related to what we want to do is this one.
Yeah, I mean, I don't think there is an actual scalar whose scattering gives us this amplitude. The dilaton axion amplitude will have some slightly different kinematic factors. There is no, it's a kind of an auxiliary scalar amplitude from which you can reconstruct everything else.
Thank you. Yeah, I think also in particular in 1, 1 supersymmetry really isn't as straightforward. But yeah, the helpful part of supersymmetry is really that you only work with one amplitude for the whole multiplet. Okay, so these are the 4 main points that we need. And so then let's look at what our setup is going to be. So in the IR, we're going to make a couple more assumptions. So the first assumption that we're going to make is that the only massless particles in our theory are just going to be the graviton and its superpartners. So in particular, we won't have any other, for example, scalar floating around that's massless. And so we can expand the IR amplitude in the following way. So you first have the graviton exchange. That becomes this. And then you have further corrections. So for example, the R to the 4 correction would give you a term like this that doesn't have any STU dependence. But we can parameterize the rest of the space by just taking suitable polynomials, or monomials, actually. And so these are going to be our EFT coefficients that, for part of them, we're interested in. And then in the UV, what do I mean with UV here is we're going to introduce a cutoff. And in the beginning, we're going to basically say that below this cutoff, we won't have any new particles coming in. So not only do we only have the graviton and superpartners as massless particles, above that, until the cutoff, we don't have anything new coming in. But as otherwise in the UV, we only are going to assume those 4 first things that I wrote on the last board. And in particular, if we now draw the amplitude in the complex S-plane, we'll have this pole at 0. And then as of the cutoff, something could happen. We'll probably have some new particles coming in at some point. And since I don't know how many there are or what positions they are, I'm just going to denote them basically as a branch cut, though technically we know these are going to be poles. And then we have the crossing symmetric version that's on this side. So again, analyticity told us that if we only look at, that the only poles that can come in are on this real axis. And then crossing symmetry told us what the two sides will look like. Okay. So before I continue on, I want to look at our one example that we know of and love, and that's string theory. So for string theory, in this context, we have the Viersor-Shapiro amplitude. And that looks like this. So we start with a bunch of gamma functions. And we divide by more gamma functions. Okay. So let's quickly look at the 4 different points. Well, crossing symmetry is quite obvious because all the gammas come with all the different factors. And then the poles that we have all come from these first gamma functions, and they're all on the real axis. And in particular, they'll be at integer factors of alpha prime. Unitarity is a bit hard. You can't just read this off of the amplitude, but that's been checked rigorously. And especially, it's easiest to see from the world sheet. And then, of course, the last one is Reggie behavior. And one can look at, in this limit, the string theory amplitude goes as s to the minus 2 plus alpha prime u, where we have already said u should be negative. In other words, this satisfies our Reggie behavior, but just barely. And so the last thing I want to look at is its spectrum. So if we plot against our mass, or J, or mass is also S, anything, we can write down a graviton pole, which we'll just put right here. It's effectively at spin minus 2. And then what we'll find is that it has a leading Reggie trajectory, so we'll have a first scalar, oh dear, at mass 1, if we normalize it against, or 1 over alpha prime. And then we'll have a bunch of other states increasingly. And then we'll also find subleading Legge trajectories. So this is the first one that includes the graviton, and then we have a bunch of subleading Legge trajectories. And I want you guys, if you haven't seen this picture before, to remember this. Okay, so let's go back to our original problem. And as I just want to mention very quickly is that this amplitude satisfies all the assumptions we're making, but we're not using anything else other than those assumptions that I just stated. Okay, so let's start deriving what we've called sum rules. So if we draw the amplitude in the complex plane again, and we want to look at the following contour of ds over s of the amplitude against this kernel. Where, let's use red, this is a circle at infinity. Then this will have an extra pole at minus u. And as long as k is, let me make sure I get this right, exactly, larger or equal than minus 2 here, because of the Legge behavior, this will converge. So that when the next thing we can then do is collapse this contour. As the following. So we have 2 pieces that wrap these branch cuts, and 2 residues from the poles. Okay. And what I'm going to do, this is important, what I'm going to do is now take the 2 poles on one side and take the 2 branch cut pieces onto the other side of the equation. So the poles are just the residues at s equals 0 and minus u, and of the expression that we had beforehand. But this will then be equal to, I'll write it down here, because of analyticity, this is related to this. And so we can write this down by crossing, thank you, see, as an integral. And this will be picking out the imaginary part of the amplitude. So this imaginary part we saw in the very beginning of the talk, and this imaginary part was related to our spectral density, and the spectral density was positive. And in particular, if you look at this, above m squared, the cutoff, all of this will therefore be positive. And therefore, we can write this as, or we'll first denote it as a heavy average, but we can use this to find bounds in a second. So why did we choose this kernel in particular? Well, this kernel, because here we have an IR amplitude, we can now pick out the different UV coefficients, IR coefficients from the amplitude. So I'll write that down now. So if you had taken k to be equals -2, you would have found the following sum rule. And k being 0, you could also continue this on, but we'll start with these two. You find okay. So let's look at this sum rule first. In this case, we don't have any poles in U, and that just means we can then use the forward limit, in other words, expand around U equals 0, to extract these individual coefficients. And so we find that G0 is just given by the heavy average of 2, and G2 is given by the heavy average of 1 over m to the 4. On the other hand, we can't do this for the above one. And so what we're going to do instead is take what was called smearing. And so this was developed first in a paper by Leonardo, David, Simon, and Dalimil. And what they did was to smear this kernel against suitable test functions. And if you increase this, and basically you can truncate choose a basis, truncate it, and the larger basis you take, the better numerical accuracy you get. So it's against suitable test functions. And you do the same for the other side of this equation. Okay. So now we basically have some rules for all the different parts that we want to look at. And we will be normalizing against this 8 pi g Newton. And so what we want to find is bounds on normalized coefficients that look like this. And then factors of m, the factors of the mass are used up by the cutoff. Oh, no, okay. Yes, so crossing symmetry came in the fact that we could earlier that we could basically map this branch cut onto this one, and that's related, and have one single expression related to the imaginary part of the amplitude. Okay, this should be a 6. Not that that was very important. And we could do the same for all the other EFT coefficients. So this is not all we can do. And basically, this comes from the fact that our IR amplitude was manifestly crossing symmetric. But in the UV, we didn't actually write down that this amplitude had to be crossing symmetric, other than the fact that these two branch cuts map to each other. And this basically means that we end up with what are called null constraints. And these are effectively, if you take an crossing anti-symmetric kernel, this will basically kill all of the IR components of the amplitude, but we'll get something non-trivial from the UV components. So this can, for example, look like, and we'll have a whole basis of these, something like this. So this is roughly the first one that you get. And keeping track of these and including these into the numerics is the important reason why we get bounds that are so good, that get us past the just analytic bounds that you'd get. Yeah? Can you just repeat that? It was very... Yeah.
But you could, in principle, have expanded around some negative value of u.
Yes, that's been tried, but it doesn't converge very well, basically. It doesn't lead to, the numerics don't work very well in this limit.
Do you understand why? Because I would have thought that the convergence would work very well if u was sufficiently negative.
Yeah, I didn't do this numerics. I don't know if there's a reasoning other than the fact that...
So this is exponential in J, and then numerically it has some trouble dealing with that, because like you're imposing positivity very large J, and it seems to not work so well with SDPB, with the current setting. But that, I don't know, that's a naive argument why.
Okay. Any other questions about setup before I get to pictures? Kellyanne had one.
Yeah, when you smear up to u equals 0.
U equals what?
U equals 0. U at 0.
Yes, I go from 0 to basically
yes.
the cutoff.
But you have to be careful when you smear up to u equals 0, because there, the sum rule, you violate Rayleigh behavior, right?
Yeah, so at this point, that's somewhere where basically what I hid in the suitable wave functions. You can't just use any polynomial, for example. You do have to make sure that this would converge, basically. And yeah, if you basically need high enough powers of u to smear against.
Thank you.
Cool. Okay, we'll first start with a relatively boring bound on the EFT coefficients before we do some more fancy stuff with the spectrum. So let's try to find a bound on G0 versus G2. These are the first two EFT coefficients. And this looks a bit like this, where at first we have a very straight line, and then we have a plateau area, and this is a schematic of what the actual thing looks like. In reality, it's a lot more thin and horrible to draw. And on the bottom, the lower bound is curved. So we kind of have three different regions here. And the first one, or let me attach some numbers. Oh, God. Here we go. And this first section, where it's linear, is easy to understand, because we have these two sum rules that look like this. So if you had an amplitude where all the particles had its mass at the cutoff exactly, then these two amplitudes would just be half of each other. And this line is exactly that. So you get exactly that G2 equals half of G0 on this line. And this is what we call a tower of states amplitude. So the spectrum for this looks like this. We have a graviton pole, and then at the cutoff, we have a tower of states that goes all the way to infinity. But we'd like to understand the rest of this plot, first of all, and I'll have to defer that for later. But in particular, we also don't like this kind of amplitude, because amplitudes that have an infinity number of states as single mass will destroy locality. So we would like to rule such amplitudes out. And the way we want to do this is by imposing by hand a spectral assumption. And so what we want to do is basically impose the opposite of infinity. We want to have a finite number of states, and the best way to start is with 1. So what we'll be imposing is that there's a single or a very small number of states at the cutoff, and then set the cutoff higher. And I won't show the plot for this, but it turns out that the only state that's allowed, really, is a mass zero state, spin zero state. In other words, a scalar. And so this is a scalar in terms of the effective amplitude. So technically, this would be including the whole supermultiplet of the scalar, but in terms of the effective amplitude, we only have a scalar. So what we'd be looking at is we want to, of course, impose our graviton pull. And then we want to impose a scalar at a mass that will normalize against. And above that, we'll choose a cutoff and then say anything can happen afterwards. So this is a slight redefinition of what we mean with the cutoff here. And so we can easily do this. And we just do this by introducing a separate pole for the scalar. So we had our first two little poles. And then at the mass of the scalar, we have a scalar here, and it's dual. And then the cutoff only starts farther up.
Sorry, perhaps you should emphasize that the fact that it's a scalar came from the numerics. It was not.
So it's not surprising that we are finding that we need a scalar, just because we had originally explained that the reason we wanted a slightly better than spin 2 behavior was that we're expecting things to regicize, should never say that word again, but we did also test out that you could, instead of having a scalar here, you could have a, let's say, only singular spin 2 state or singular spin 4 state, or a combination thereof, a spin 0 and a spin 2. And what we basically find from the numerics is that only spin 0 survives. And adding multiple other states doesn't help.
Can I also ask, could you explain a bit more why the previous spectrum with the Regge trajectory in the wrong direction would necessarily violate your locality? What's the mechanism?
Evenly, you need an effective Lagrangian with infinite non-local in the sense of infinitely many derivatives. You have, if you look at the amplitude at the pole in S, you have something which is non-polynomial in T. Yeah. So that's it's. Nice. Have you ever seen anything like that?
No. I mean, yes. The previous slide.
I think it's a very reasonable axiom. Now, Kuhn has accumulation points, that's a different story, but it doesn't have infinitely many spin at the same mass.
Could they couple like suppressed in spin, like larger derivatives have a coupling which is more and more suppressed?
I don't know. I think as assumptions go, I would say it's a very mild one. But
either way, we'll also go back to this first plot, and we'll basically be able to understand the rest of the plot through this. So us assuming that there's only a single spin at this point basically just means we're taking out this one amplitude that we already know what it looks like. Okay. So we can now have this additional scalar, and we can give it a coupling that we'll call lambda phi squared, and we can insert it into our UV components of the amplitude. And so now we can basically rerun all our numerics, but we have a new variable that we can bound, and that is this coupling of the scalar. And we can do that here. Okay. So the first thing we would like to do is look at the scalar coupling on its own, ignoring the EFT coefficients, only looking at the scalar together with the graviton pull. And we'd like to look at its bound as we increase this cutoff. In other words, when we're increasing this cutoff, we're basically saying that the more it's increased, the less there's not allowed to be any particles that come in between this first scalar and the cutoff. And because of that, we already know that our bound has to be monotonically decreasing. But it has an interesting shape. So we'll plot it against this new cutoff normalized by the scalar mass. And so we should be starting at 1. And we find that there's a maximum value it has, and it continues on, and it falls off very quickly as of a point. And this point is at 2. And it's roughly here, it's like 3. But this maximal value is roughly 1.27. Why do I give this? Because at this point, we can now look at where string theory falls. And as I already said in the very beginning, when we looked at the plot of its spectrum, string theory also had a very first scalar. But that scalar had a coupling that was equal to 1. And so string theory lies here at 1. Okay. But this is interesting, because now we basically find that there must be an amplitude that maximizes this scalar coupling, but it also tells us that it must have a second state, or more than states, at mass 2. And so we can now look at, well, what does the spectrum look like of this? Nice. Okay, so we can usefully try to extract the spectrum from S2B at this point. And other than the 2 points that we've put in, we have a cutoff that's now at 2. Let's actually add some labels. And we find a bunch of stuff. Here, we also find, okay. So this looks interesting first. And the first thing you can definitely see is that you find something that looks regitrajectory-like. But then you're a bit concerned about all the stuff that happens above it. But this tends to be a feature of SUB spectrum extraction. So what we can do is try to clean it up a bit. And so the idea is basically is that we shift this cutoff dependent on spin. And if that doesn't change the bound on our scalar that we have here, then these states must have been numerical artifacts. And so we can do that. And the spectrum, the best spectrum that we can find without lowering this bound, looks like this. Okay, roughly. I am not very good at it. You'd have to look at the actual thing. But then the cutoff that we use for this will basically be this. So we find that this also has the same bound or same value of the scalar as the previous one, which is equal to that plateau value. And so our hypothesis is, we have some double points here that we're assuming are numerical because you have to truncate the null constraints and stuff like that at some point. But our hypothesis is that this extremizing amplitude has a single regitrajectory. Okay. So what was interesting is that we basically only imposed a single state. And after imposing a single state, we got an infinite number of them for free.
So are the residues small anyway, the residues for these poles that you exclude?
I didn't understand the question.
No, the couplings of the poles that you exclude, are the residues small anyway?
Are they what?
The residues.
The residues.
Oh, yes, but it's harder to take from the spectrum. The problem is that they end up being comparable to other ones that do lie on the spectrum. I find it very hard to look at the couplings and exclude them immediately from this point.
Ah, okay.
Yeah.
Take only one scalar in both. If you take only one thing below the cutoff. Sorry, so the question is, how are these two plots different if you take only one scalar below the cutoff in both of them?
So the idea in some sense is that the physical part that we've input, that we just have the graviton pole and the scalar, that stays the same. And they both have, oh, that's right, fine, this maximal value, which is roughly 1.27. And this is the case here too. But in this case, we've basically given the most freedom for STBB to basically put poles wherever it wants to. And in this case, we're like, well, which one of those were really relevant to the numerics? And we find that if we try to basically exclude more and more of those poles by increasing the cutoff dependently on the spin, then we find that if we push this any farther, the bound will drop. So this must be where the relevant ones are that are important for this bound. We've also done some small searches of trying to exclude areas down here. And again, that didn't change anything to the bound, though it starts to get significantly more unstable numerically once you try pulling that up. Okay, so, well, now we have a first scalar. And the next thing what we'd like to look at is how does this affect the EFT couplings that we had in the beginning. So let's start with a single EFT coupling. And so what we want to do is we'll take the first one, we'll keep lambda phi on the same axis, and look at its effect on G0. And the thing we find is interesting because we find a convex hull just spanned by 3 points. Oh dear. And so, okay. And in particular, this amplitude that we had that maximized this first scalar is right here. And it also maximizes our bound on G0. So this is our single Reggie trajectory theory. And also, these are all straight lines, despite its appearance. Down here, we can basically find a kind of boring, quote-unquote, amplitude, because if you take alpha prime goes to 0 limit in the Virasoro-Shapiro amplitude, you basically just get a decoupling of the graviton pole, the 1 over STU, and all the other states get pushed to infinity because their masses were all 1 over alpha prime. So you basically get something that has no scalar in the beginning, and it has 0 EFT couplings except the graviton pole survives. So this would be a very boring, to some extent, UV completion of just supergravity. But let's try to understand this third point that we have. And it's a bit weird because it has no scalar, but it has a EFT coupling that's non-zero. And the next thing we can do is, well, let's look at the next higher mass. And one thing I should have mentioned is at this point, the cutoff against the mass of the scalar was set to 2 because we wanted to look at what happens at this single Reggie trajectory point. And so let's start looking at what kind of particles can come up at mass 2, and let's start with a scalar. And we find an interesting behavior in that here we have no scalar at 2m phi. And this makes sense because this one had just the graviton pole and nothing else. And this one is a single Reggie trajectory, and its first state at mass 2, or 2m phi, is a spin 2 state. But then you can plot the coupling of the second scalar, and you find that it's constant along these trajectories and goes up linearly, and the second scalar, 2, has a max value, something around this, and this was the scalar at mass 2m phi squared. So what we're finding is that this point is described by basically an amplitude that must have no states at mass 1, if we normalize it in a certain way, and then it must have states at mass 2, which is a bit weird. But again, we can play this game where we try to look at the spectrum. And you have to do a bit more work for this. And in this case, I'll only draw the spectrum after we've taken a bunch of these numerical poles out. So we've run the same game again. So we have here, we have the graviton pole. Then here, we have nothing. But we have a scalar at mass 2. And then what we find, roughly, is another linear Legge trajectory. But it's shifted by 1 over compared to that of the graviton. So what we understand here is here we have this shifted single Regge trajectory. Amplitude. Okay, and so finally, we can use our knowledge now and go back to this original plot that we had of G0 and G2. So let me draw that down. Okay, so the original one looked like this. Oh dear. And now let's again make this assumption that we take a scalar, but with possibly infinitesimal coupling, and then take the cutoff at 2. And we find that this reduces the amplitude, or the plot, to this. Okay. So as expected, this tower of states amplitude we had in the beginning was ruled out just by construction. And we find, as we found earlier, that this point that we had earlier is our single Regge trajectory theory. And then we have a third point right here, and this will be equal, this will give us the shifted one. And here we just have the alpha primes goes to 0 limit of string theory, or any other theory, basically. So now we can understand, or at least conjecture, what's happening along this rounded border. Because basically, we have, it must be a family of theories, because it's continuous. And we have a single Regge trajectory, and at some point, we get a shifted Regge trajectory, and at some point, nothing happens. In other words, what's happening as we go from here to here is we must have a theory that has a graviton pole and a single Regge trajectory with fixed slope. And as we move upwards in this case, it moves closer and closer towards the graviton pole. Once we get to this point, it gets excluded in this area by our assumptions that we made, saying that our first cutoff must be at 2. But we recover it again with the single Regge trajectory that we had, and that's the farthest it can go. And then this third line, which is basically straight, is just the linear combination of the extreme point of the tower of states amplitude with the single Regge trajectory.
Do you understand why the shifted trajectory is not just the same trajectory but with slope 1/2?
Yes. So you could, we did ask that a lot of times. So you could do that, and you'll find, this is, I think, easier on the plot beforehand. You'll find, if you take this and you were to rescale this so that the slope changes as well, you'll end up roughly here. So it's inside the bounds, which is good, but it's not the actual slope. And if you think about the shifted version, once you rescale it, it goes too far and gets ruled out by the assumptions we'd made. Exactly.
So the one with the 1/2 slope does not maximize the coupling.
Exactly. It doesn't maximize it in that way. Yeah.
Okay, thank you.
Okay. So are there any questions? Yeah. Yes, exactly. I mean, this is the only thing we've really input by hand was the fact that, well, it was the first scalar that we put in to set a scale. And the second one could, in some sense, hypothesize is that we decided, or we said that the Reggie behavior must be better than spin 2. Kind of thing. So if they're very much linear. There's a couple like extra little daughter points that come up. But we believe that those are probably just from the fact that we have we've truncated our set in the numerics. Kind of thing. But we didn't try to rule those out as well, just because they came in at higher up. The very first ones are very much, if you look at the exact masses, they're exactly on top of it. But as you get higher up in mass and spin, it starts to get, slightly different. But I think that's just because of the truncation. Okay, so just to finish off, because I think I have 3 minutes left. 8 minutes left. Well, that's exciting. So I'll quickly just very briefly discuss what we tried to do analytically. And the key word here is tried. And in particular, one can now see if we could construct a theory that has, or an amplitude that has a single Reggie trajectory. And what one can do is that there is an amplitude that we found in a paper by Nima and collaborators, and that looked a bit like this. So it started off with the Virasoro-Shapiro amplitude, and it added, well, I guess subtracted, something that looks very similar. Oh dear. Okay. So this looks very similar if you remember the Virasoro-Shapiro amplitude. And it's basically the same thing, except for here you basically have added 1 digit to the number in the beginning. And so you have a certain thing, and Nima found that this is unitary in this range. And so if we look at this on our plot, and I'll start drawing them. We have string theory that's somewhere here in the middle. And then we have this additional amplitude that goes something like this. And what we found from the numerics is that it likely will extend slightly back, roughly until probably -3/16, at which one of the scalars becomes 0 and then negative in coupling. But now we could use this as kind of motivation, because then the question is, well, if they added 1, why can't we add more or change the difference? And this was also done in actually a paper by Kalyan and Sesha, where they did more of a primal bootstrap approach to this. But one could set up a whole basis of this, where you basically sum over with some coefficients, things of the sort S, oh no. Oh. Okay, so you could have basically where you change the coefficients, possibly slightly different, so that you add the crossing symmetric combination, and you now have a huge basis with which you could now try to basically play a game where you use all these different terms to subtract away all the different particles that are below the leading Reggie trajectory. And we tried playing this, but this is not an easy game to play because there's actually under-constrained because we have too many parts here. And on top of that, you need an infinite sum of them. And this very quickly becomes tricky because then it gives you certain other branch cuts that possibly happen. But we did succeed to find one amplitude. And I will erase this. That looks to be unitary. And this is, in some sense, this is inspired by an amplitude that was done for open strings by Cliff Chung and Grant Remen. But again, you start off with the Virus or Shapiro amplitude, and you multiply by a hypergeometric function that has the same factors as you have in, as you have in the actual Virasoro-Shapiro amplitude. Plus a single variable that we've called x. So let me just finish this. And this takes us in a slightly different direction in that this goes roughly here, but it doesn't get all the way to the end. So I think this approach will still need some work if we're going to try to find these, well, not this one, but the single Reggie trajectory amplitude and possibly even the whole family of states that we're trying, that we found numerically. But yeah, that was our first approach analytically, and I think it needs more work. We'll need more work in the future. But yeah, so otherwise, we're not saying that the single Reggie trajectory is probably from a completely whole and perfectly nice theory. It's probably just a part of the numerics. And our hope is that, in particular, as a follow-up project, to try to take this as a, basically take a system of amplitudes in which we also take, for example, the scalar that we've imposed as an external particle and try to see if that will rule out these and then close down to string theory. Thank you.
So are there any questions for Waltraut?
Sorry, why is the argument of your 4F3, why is it 1? Why couldn't you put any number and see what you get?
Okay, so basically the way this part works is that you basically, this will have certain residues, and the 4F3 has basically the opposite residues. So it cancels those and replaces it with other polynomials, but it's very hard to make those polynomials equal to just single Gegenbauer polynomials so that you'd end up with a single Reggie trajectory. So you basically have some expansion, a very different expansion in polynomials, which gives you a different spectrum. But the spectrum, in some sense, looks the same as the one from string theory, but has completely different couplings.
By the way, can you remind us what is x?
Yes, so this, there, probably should come with it. So x is basically a free variable, and we believe that it's unitary, again, in a 0 to 1 range. Type thing. Outside of that range, certain couplings become 0, and we haven't tested this in other ways than just testing the first 40 spins, or actually not higher, 40 masses, so roughly 80 spins. But yeah.
Thanks. More questions? Yeah.
Yeah, for Chung and Remen, they realized that this amplitude was actually a 5-point amplitude with special kinematics. Is it also the case here?
This one here
Yes.
down below, I do not know. We didn't do any more other than inspired guessing at this point.
Thank you.
I would say. So yeah, maybe one could try that for sure. Thank you.
More questions? I think nobody heard that.
These 4F3s evaluated at 1, sometimes there are some 9J symbols. Do you have any kind of comment on that? Or?
With rational entries for A and Bs. The 9J symbols usually have rational entries, like half integers, and these are continuous parameters.
But for the non-compact group?
Ah, yeah, non-compact.
I'm not quite sure I understood the question though.
Sorry?
I didn't quite understand. You were asking about this.
I was just asking if maybe there is some representation theoretic significance of this coefficient that you explored, or.
Oh, no, I wouldn't know basically. Okay. we really, I mean, it was definitely inspired, and the hope was basically the original thought was to try to take the Virasoro-PR amplitude and really, as I explained beforehand, basically to divide by its own residues, so that you take out first all the states and then multiply effectively by something, that thing. So you can rewrite this again as a sum of all those terms that I had written, but it's a very special sum. And if you just choose a random sum, the answer that you get either can't be resummed, or the resummed answer isn't a well-defined function.
Thanks.
So the fact that there's one trajectory, we saw something similar earlier in the conference for conformal bootstrap, that there's for single correlation function, there's some expectation that you get the rigid trajectory with external operators, and then you need to go to multiple correlators. Is there no relation, or conversely, are there examples in this setup where you get multiple rigid trajectory, like the daughter rigid trajectory in the correct direction from a single scattering amplitude?
None of the extremal amplitudes that we've found have more than a single rigid trajectory. So I wouldn't call that evidence in some sense. Of course, what we did do is at one point is when we looked at the second scalar, that's when you did start seeing evidence of a second trajectory, because if you put here, if you take string theory, which actually falls, if you look at the line that string theory falls on, it's exactly the value that string theory has. And you could do this with all the other, the 4F3 one or the Nima's amplitude. You could do that as well and look at more of the whole spread of them, and it'll always fall on the same one.
More questions? Any final question, maybe? Okay, if not, let's thank Waltraut again for the nice talk. So another announcement, tonight, starting from 8 p.m., we will have the reception in the place that I mailed you a couple of days ago. So you're all welcome to come. If you don't remember the place, just email me, I will email you again, and I'll see you there. Thank you.